Hi there. Let's finish our tree diagram and see if we can answer this question. So the other three branches of the tree diagram are found by multiplying by the probability that the antibodies are present times the probability of a negative test, given that I already know that the antibodies are present. So notice that along this tree, this right here is a conditional probability. This is the probability of a negative test given that antibodies are present. And the reason that that condition is important is because that is the condition that precedes it on the tree. If you follow this branch backward, this branch actually came off of the antibody branch. That probability came first. So this really is the probability of the antibodies being present times the probability then of a negative test, given that I already knew the antibodies were present. These probabilities then together make the probability of antibodies present and a negative test. So I really can just multiply these together along the branches of the tree in order to complete my table. So the 0.01 times the 0.0015, that gives me 0.000015. Something to think about. On your calculator, we got 1.5, and then this e to the negative fifth, that really means 10 to the power negative 5. That means we need to move our decimal back 5 places to the left, so that's how I got to here. So multiplying my next two probabilities together, 0.99 for no antibodies, 0.006 for a positive test given no antibodies. That looks like 0.00594. And in the last branch, I have no antibodies, again at 0.99, times the likelihood of a negative test given that no antibodies were present. That's 0.994. 0.99 times 0.994, that looks like 0.98406. So notice these four outcomes are disjoint. In other words, either antibodies are present and you get a positive test, antibodies are present and you get a negative test. There are no antibodies and a positive test, no antibodies and a negative test. There are no other options. So if you add these four probabilities, indeed their sum is 1. So this is all that there are. All the options that we have from this tree. So ultimately, our goal was to find the probability of a positive test. So understand two of these probabilities involve a positive test. That would be this test, so antibodies present and a positive test. And then down here also, no antibodies present and a positive test. So to actually answer the question, what I'm ultimately interested in finding, the probability of finding a positive test, that is 0.009985. That came from up here. Plus the 0.00594. That came from here. And again, I can just add these two together. There is no overlap. These events can't happen at the same time. So this is antibodies and a positive test, but this is no antibodies and a positive test. You either have the antibodies or you don't. These are disjoint, so I really can't add these together. It's important that we do so carefully with all of the decimal places. That looks like 0.015925. So that is the likelihood of a positive test. It'll happen about 1.6% of the time. So now notice only 1% of the population actually carries the HIV antibodies. So if I'm randomly testing someone from within this population, 1.6% of the time I'm getting a positive test. I am getting some positive tests when in fact there aren't any antibodies present. That's something to think about here. So something that's important then in terms of the decision making that you make with your doctor is this. After you get the test back, if you are a patient and you actually get back a positive test result, what's the likelihood that antibodies are present under the condition, given that you've now seen a positive test? So this is This is an important calculation to consider, and notice this is why we had to find the probability of a positive test, because we needed to use this to do this calculation. So if you bear with me a second, I want to take a minute and motivate where this calculation comes from. So take a look. On the front side, we were doing calculations that look like this. The probability of having antibodies and a positive test. That probability and a positive test. So that can be found by taking the probability of a positive test times the probability of having antibodies given that the test is positive. So understand, I'm rearranging the calculation a little bit. The probability of both having the antibodies and a positive test, that's the same as having the probability of that positive test times the probability of the antibodies, but given that the positive test has already occurred. This is what I'm really interested in. This is what I'm trying to find right here. The probability of the antibodies being present given that I've just been given a positive test, I've seen a positive test result. So in order to do this calculation, this is what the general multiplication property allows us to do. But to find the conditional probability, all we need to do is divide by the probability of a positive test. Here's where I got the formula. So take a look. To find the probability of antibodies given a positive test, that's what I'm trying to find. All I need to do is take the probability of antibodies and a positive test. Here it is. So the probability of both, and divide by the probability of what's already been given. I've been given the positive test result. So to do that conditional probability, here we go. The probability of antibodies and a positive test, I can get that from the front side. So here it was. The probability of having the antibodies and having a positive test is 0.009985. So there's the numerator. Now, this is under the condition that a positive test has already been seen. So the likelihood of a positive test is what we calculated on the front side. That's what all this work was about, the 0.015925. That ratio then is going to give me the probability that I seek. The 0.009985, if I divide that by 0.015925, that gives me this probability. So if you click on the next video, we'll take a second and interpret what that actually means, because that's important. We'll summarize this.